Assalamu alaikum and welcome to lecture number 31. In this lecture, we will continue the topic of the Laplace transform. We'll talk about the poles and zeros, and we also talk about the properties of ROC. For a rational Laplace transform, we can write here ns is here ns is the numerator polynomial, whereas dA is the denominator polynomial. X of s will be rational whenever x of t is linear combination of real or complex exponentials. So we can write x of s as product of terms involving the roots of denominator and numerator polynomial. The generalized form is as, so we have b of m, the scaling factor, and then we product k running from 1 up to m, s minus ck. This is the numerator polynomial, right? And we can also write the similar expression for the denominator, and we say k running from 1 up to n, and we're taking, you understand, this symbol is for product, right? Product s minus dk. So this is for the denominator polynomials, right? So that's the generalized expression. So that means we can represent it also by the polynomials. So then we define two terms, that is poles and zeros, and we define the pole, that we say for a rational polynomial the roots of numerator polynomials are commonly referred to as zeros of x of s. That means for example if we have product of two, for example if we have a Fourier transform, Laplace transform, which consists of which is x of s, and it is equal to s minus c1. We are taking product of terms s minus c1 multiplied by s minus c2 divided by s minus d1 and s minus d2. So for poles is the values of s when x of s equals to 0. So what values of s are there which makes it 0? So they are called zeros. So if I replace s equals to c1, so in this case this will simplify to 0. Similarly, right, that is we have zeros, right, and these are s equals to c1 and s equals to c2. So we have, in this case we have two zeros, right? So if s equals to c1, so you see c1 minus c1 0, so 0 multiplied by anything 0, and divided by this will also result into 0. So we get the first 0 when s equals to c1. Similarly, we get the second 0 when s equals to c2, right? So I understand for zeros x of s will become 0. This signal will become 0. Similarly, there is another term that we call it a pole. So poles are the values of the denominator polynomial, and at poles we have x of s equals to infinity, right? So that means if for zeros, let me write here again, it's okay. So for poles I can write that poles we have, you understand, when for this particular case when s equals to d1, so we have d1 minus d1 equals to 0. So 0 multiplied by this will be 0, and this divided by 0 will be infinity. So as we have defined here, that poles are those values of s for which x of s is infinity, right? So we have, again, because we have two terms here, so we have two poles, one at d1 and the second pole at d2. right? So we can also express x of s in terms of poles and zeros. So poles and zeros gives the locations of poles and zeros in S plane uniquely specify x of s, except for the scaling factor, right? This is the scaling factor. So except this one, it uniquely specifies the x of s. So using this, we can also specify the Laplace transform, and you understand, except with the scaling factor, it's completely specified by the poles and zeros in the S plane. Okay, so you understand what is S plane. S plane, if I write it, so it is something like this is your S plane. So in S plane we have, or maybe let me plot it on the next slide. So for example, this is the S plane, right? So this is, you understand, sigma are real, and this is the imaginary, right? So S is a complex plane. You know that we have already discussed that on the vertical axis we have the j omega. Our vertical axis is basically imaginary axis, and the horizontal axis or x-axis are the real axis, right? So for example, we have two poles. uh, okay, so you understand poles are represented by the cross signs. Okay, so for example, we have two poles, one pole here, one here, and similarly again we have, for example, we have two zeros. So one zero is here and one zero is here. So using these poles and zeros, we can completely uh, specify x of s, and you understand, except with the scaling factor, right? That is bm. So this is how we can represent it. You understand, if you look at the s plane, it is. So we can also say that if x of t is absolutely integrable, then we may obtain the Fourier transform from the Laplace transform by setting sigma equals to 0, because this axis is your Laplace Fourier transform, this one, right? Because you see, if you move in this direction, sigma is positive, and if you move in this direction, sigma is negative, but at this point it is 0. So because in the Fourier, you understand, we have while we were starting the discussion on Laplace transform, we said that in case of Fourier transform, we take the real part as 0, right? So we can write that x of s, basically, right, for those signals that are absolutely integrable, x of s equals to x of j omega. And where this happens when sigma is, right? So we can say, okay, provided sigma equals to 0. So when sigma equals to 0, that is real part equals to 0, in that case the Laplace transform is basically equal to the Fourier transform, and this will happen only when the signals are absolutely integrable. This happens when the real part is 0. So we can say that Fourier transform is given by the Laplace transform evaluated along the imaginary axis, along this axis, because for Fourier this axis is 0. So we are only along the imaginary axis. So you can see that this j-axis or imaginary axis divides this whole plane. Let me take the pointer. So the imaginary axis divides this plane into two halves. One is this one, right half, and one is this left half. The region of the S plane to the left of the j omega axis is called, it is also called the left half, right? This one is the left half plane. Similarly, the region to the right of j omega axis, this is called the right half of the S plane. The real part of S is negative in the left half of the S plane and it is positive in the right half of the S plane. Okay, so let's do some numerical problem to clear the idea of how to find the poles and zeros, right? Remember, to find the poles and zeros, we need to express x of s as product of terms involving the roots of denominator and numerator polynomials. So for example, we have a function x of t equals to impulse of t minus 4 by 3 e power minus t u of t plus 1 by 3 e power 2t u of t, right? So to plot the poles and zeros for this, first we need to find the Fourier transform of this function. So we know that x of s equals to integration minus infinity up to infinity, right? And because we have this whole, so it will be applied on term by term. So that means we have impulse of t times e power minus st d of t plus. So applying formula on all the terms, we understand because we have u of t. Okay, so we have u of t, so that means the integration will be from 0 up to infinity, and similarly for the third term also, right? So once we find this limit, so I hope you understand, for the first term I'll get 1, and we have region of convergence for this one all S plane, right? So for the impulse we have region of convergence, which is all S plane. For the second term we have minus 4 by 3, and we have 1 over S plus 1. So for this one, region of convergence, we understand, will be real of S should be greater than minus 1, and plus the third term, so we have that's 1 by 3, and the expression is 1 over S minus 2. So for this third one, the ROC is for S real of S greater than 2. So that means the overall region of convergence for this will be, we can write it like ROC. Okay, let me change the color, and I write, okay, ROC will be, right, real of S, okay, and it should be greater than 2, right? So for the first term, you understand ROC is all S plane. For the second, it is greater than minus 1, and for the third, it should be greater than plus 2. So overall ROC for this x of S will be S greater than 2, right? So let's write it in the as a product of terms, right? So that means we have x of S equals to taking the LCM. So LCM for this, it will be s minus 1, s plus 1 and s minus 2. Okay, so this is the LCM. On simplification, we get s minus 2, and here we have s minus 1 whole square. So this is the expression in of x of s in terms of product of terms, right? So we find the zeros. So to find the zeros, we know so at s equals to 1, we have, I hope you understand, you replace s with 1. So if I write 1 here, it will be 1 minus 1, 0 square, and divided by whatever you get, so it will result into 0. So we have, in fact, 2 zeros, right? In this case, we have 2 zeros at what position? At 1, right? So here they are indicated. We have 2 zeros at position 1, s equals to 1. Similarly, to obtain the poles, if I replace s with minus 1, so you understand, minus 1 plus 1, it will result into 0. 0 multiplied by this will result into 0, and this one divided by 0 will result into infinity, right? So you understand, the poles are the values of where x of s is infinity, right? So we have, in this case, we have 2 poles. One pole is right, you get infinity for this when s equals to minus 1, right? And similarly, when s equals to plus 2, again at s equals to plus 2, that you understand, 2 minus 2 will result into 0, and this thing divided by 0 will be infinity. So we have another pole, so which is at s equals to 2, right? So here they are marked on the complex plane. So we have pole, right? And you understand, pole is represented by the cross sign. So we have, in this particular example, we have 2 poles and 2 zeros, right? So one pole is at minus 1, and second pole is at plus 2, whereas in case of zeros, we have 2 zeros at plus 1. Okay, so we have 2 poles which are located at s equals to minus 1 and s equals to 2, and we have 2 zeros which are both at s equals to 1, right? So if you have, for example, cube here, then we'll say, okay, we have 3 zeros at s equals to 1. So I hope this gives you idea of poles and zeros. So the next topic we are going to consider is the properties of ROC. I hope you understand what is ROC, right? So the ROC of x of s consists of strips parallel to the j omega axis in the s plane, right? We have done this. Maybe I just draw one. For example, this is your s plane. You understand, here we have sigma and here we have j omega. The vertical axis is basically imaginary axis, our j omega axis, and horizontal axis is the real axis, are the sigma axis, right? So the ROC, for example, for some signal, if we say ROC, right? Let's take some of the examples we have already done, and we say, okay, for some case we have S of real. So this example we have already done. So for example, for any particular signal, we say ROC is, okay, you know, that's the definition, that real of S should be greater than, that's what we found, right? So real of S should be greater than minus a. In that case, for example, this is your minus a point. Okay, this is your minus a point. So these are the strips. Okay, so this all region, right? to the right is the region where it will converge, whereas for the real of s less than minus a, it will diverge. Okay, so this is your region of convergence for this particular case. Okay, so the ROC consists of strips parallel to the j omega axis. You understand this is your j omega axis and these are the strips, and you can easily see that this is basically parallel to j omega axis, and this whole thing, you understand, this is called the S plane. For a let me take the pointer. So for a finite duration signal, the ROC is entire S plane. For example, you have just found in the previous example that you have impulse. So in case of impulse, we have the impulse is the finite duration signal. So the ROC for it is the entire S plane. You can see the example this we already done in the, I think, one slide back or so. Hence, the ROC of a general signal x of t remains unaffected by the addition of any finite duration signal, right? So like in the previous example we did, it was right, it consists of three terms. If you recall, that was one was the impulse and other was the scaled exponentially decaying and growing signal respectively. So you see that in case if we add right impulse to it, so the ROC for it will be unaffected, right, or not affected. Okay, if x of t is right-sided, right, and if the line is real of s equals to sigma naught is in the ROC, then all values of s for which this condition is met will also be in the ROC. Okay. Similarly, if x of t is left-sided signal, right? So you understand left-sided and right-sided that exists from right up to 0, and to the minus side, that is your left side, and right side is from 0 up to the positive side. So that's your right-sided signal. And if the line of this is in the ROC, then all values of s for which this will also be in the ROC. Okay, so maybe we do some examples to explain or to grasp the idea of these points. If x of t is two-sided, right, that means it exists on both axes of time, and we have its region of convergence equals to sigma naught is in the ROC, it's a point, right? Then the ROC will consist of strip in the S plane that includes the line, this one. Okay, now for a rational Laplace transform, ROC is bounded by poles or extends to infinity and does not contain any pole. We have either it will contain poles, or we can say that it will extend to infinity and does not contain any poles. Similarly, if x of t is right-sided, the ROC is the region in S plane to the right of the rightmost pole. So I think if you recall the previous example, so you can easily understand this, right? If x of t is left-sided, the ROC is the region in the S plane to the left of the leftmost pole. If the ROC of Laplace transform does not include the j omega axis, then the Fourier transform does not converge. Okay, so that's clear. So let's consider another example, and here we have x of t equals to e power minus b absolute of t, right? So we can split it into let's first write the equation for the Fourier for the Laplace. So we know x of s equals to integration, right? Now, because this is absolute value, right? So that means it's absolute, the value of the t will be negative, right? So irrespective of, right? So whether it's a positive or negative, because if t is negative, again, right, for negative, absolute is positive, and again it's negative. So that means we can write it like we have two signals for, right? That means from minus infinity up to 0, we can write this signal as e power minus e plus bt, because time is negative, so resulting signal will have negative value for t. So similarly, for the depending upon, you understand, depending upon the value of the b, if we look at the signal, depending on the value of b, it can be exponentially growing or exponentially decaying when you move from the 0. For example, if b is positive, right? So if b is positive, that means if we move from 0 towards negative infinity, it will be decaying. Similarly, if we move from 0 towards positive infinity, again it will be decaying. Okay, but if b is negative, so you understand that negative and this negative will make it positive. So that means this signal will be exponentially growing irrespective of whether t is positive or negative. That means if we move from 0 towards positive infinity, the signal is going to uh, grow. And similarly, if we move from 0 towards negative infinity, the signal will be growing, right? So that means we can write it like this, split it into two parts. So this is your part 1, and here we have s of t, right, and d of t. So that means we can split it into two. So again, I think we have encountered such signals multiple times, right? So hope you understand that. Okay, now this is 0 to infinity, and then we say e power, then we'll take minus bt, right, and times e power minus st d of t. Okay, so if we look at this signal, we can say basically this x of t consists of two parts, left side, and this is the right side, right? So it exists from minus infinity up to infinity. For the case from 0 to minus infinity, we have this expression, and for the signal that exists from 0 up to infinity, we have this expression, right? So you understand this similar question we have done. So if I straight away write its Fourier expression, so sorry, the Laplace expression, so I can write it like, right? So I think you can do it. So if you do it, then you find that its expression is minus 1 over s minus b, and its region of convergence will be real of s should be less than b. Similarly, for this one, we can find that basically this is equal to 1 over s plus b, s plus b, and its region of convergence ROC will be real of s, and it should be greater than minus b. Okay, so if I plot region of convergence for the first case, so in the first case, this is the uh, ROC, right? So that's the real part or the sigma, okay, and this here j omega are the imaginary part. So uh, for example, this here for this case, it should be less than b. So for example, this here b, okay, I denoted by cross, and you understand why I denoted, because if you simplify the two expression, you will get x of s, and x of s will be equal to, you understand, you take the LCM and those things, so you can simplify it and you will get it as 2b over, right, minus 2b over s plus b and s plus b times s minus b, right? So that is the expression if you sum the two. Okay, so we are talking about the first one. So in case of this first one, we have the region of convergence, and region of convergence for this will be something like this is your b. Okay, so if you look at the this expression, you can say that it contains two poles, one pole at s equals to s plus b is from this here, right, from this expression, and s minus b is from here. So s minus b, so when s equals to b, so that's your first pole, right? So when s equals to b, b minus b equals to 0, 0 multiplied by anything is 0, and this divided by this will result into infinity. So that means you get the first pole, right? You have one pole here and you have one pole here, right? So pole for this one will be when s equals to b, so this is your pole, right? Now again, because we say the region of convergence for this is s is less than, so the ROC will be all the values of the sigma, right, less than b. So this is b, so less than b will be all this region, right? So that's your ROC. Okay, that's not very accurate lines, but I hope it's right. So from here up to infinity, that's your region of convergence, okay, for this part. Okay, now again for the second part, we can write it like this one. And again, if you look at this one, so here the region of convergence is s real of s should be greater than minus b. So for example, that's your minus b. Okay, so for this case, the region of convergence is greater than minus b, so this minus b point. Okay, and okay, so we have one more pole here. So the pole is, if you look at the generalized expression which we have found here, so s if s equals to minus b, then minus b plus b cancels, you get 0, 0 multiplied by this will result into 0, and this divided by this will result into infinity. So in this case we have two poles, so we are talking about this second expression. This second expression has ROC defined by this, so it should be greater than minus b, so that means somehow all this region, right? This is the ROC for this second part. Okay, this part. Now the overall ROC for this expression will be combining the two, so we get the ROC will be let me write here. So the overall ROC for this signal will be, the ROC should be, because this here okay, if we combine, so hope you understand that ROC will be between minus b, right? It should be greater than minus b, and what should be greater than real of s, right? So real of s should be greater than minus b, and it should be less than, because for one case we have ROC from here up to this side, and for the other, so if we combine, then we say okay, so ROC will be from real of s should be greater than minus b and should be less than, so something. Okay, so it's drawn here because it's copy paste, okay, from the Oppenheim book. Okay, so this is the ROC, overall ROC for this particular problem. So the properties we were talking there, so you see this signal is this part of the signal is right, So this is right-sided signal, this one, right? This right signal, right side signal, you understand this exists from 0 up to infinity. So we call it right-sided signal. So for a right-sided signal, we have a right half plane, right? So that's, you see, this is this side, okay? So as we discussed in the property, for two-sided signal, we'll have a strip right here. So that's this part, right? So we have this thing for the two-sided signal. You understand, for the right-sided signal, if we look, so this whole plane is for the right side, okay, this side. Similarly, this whole plane is for the left side signal, right? And if we combine the two, so we have, because this signal is now two-sided, so for two-sided signal we have some finite region of ROC, which is in this particular case defined from greater than minus b up to less than plus b. So I hope this gives you idea. Let's see, we have a signal which is, let me highlight. Okay, so we have a signal that is x of s in Fourier domain. It's equal to 1 over s plus s1, s plus 1 and s plus 2. So that means this signal has two poles, right? And where are they? They will be when s equals to minus 1. So you see, minus 1 plus 1 becomes 0, minus 1 plus 2, that's 1, but this is 0, so 0 multiplied by this will result into 0, and 1 over 0 will result into infinity, right? So we have one pole at s equals to minus 1, and we have another pole at s equals to minus 2. So if we plot them, so as shown here, this is the plot of the two poles, right? So you understand, this is your s plane, so this is your real axis are sigma, and this is your imaginary axis are j omega axis. So this is the pole zero plot for this one, right? So by looking at just the expression, we cannot say, because this can result into different distinct signals. So for example, we assume that this plot again shown here, right, with the ROC, corresponding ROC. So you can see that Fourier transform converges, right, only if the ROC includes j omega axis, right? So okay, so let's see how three different ROCs, or three distinct signals, can be formed based on this expression. So we have pole that's minus 2, and this is minus 1. So one choice is minus 2, minus 1, and we say that the ROC is points that are real of s, right, is greater than, for example, minus 1. So you have ROC from here onward, right? So one is your ROC, this one. So this results into, this means that it includes the j omega axis. The Fourier transform of this signal converges, right, because it includes the j omega axis. So this is for the right-sided. Similarly, let's see on the next slide, it can also be ROC like this, right? So ROC is less than minus 2. So this ROC is for the case okay, sorry, not this one. In fact, if you look at this one, so another ROC will be that you say it is less than, right? You understand, this is minus 2 and this is minus 1. So we say that ROC is less than minus 1. So that means the signal is this, right? The ROC is this side. So this is basically your left-sided signal, okay? And it can also be a two-sided signal, and we say ROC is greater than -2, this is -2, and this is -1, right? So we say, okay, ROC is greater than -2 and less than -1. So in this case here we say basically this is the two-sided signal, right? Like the previous example you did, that the signal exists from 0 to -infinity and also from 0 to the positive infinity. So it was a two-sided signal, and you found that the ROC is the ROC of that was, there was the variable, the scaling in the exponential signal, that was b minus b. So we said, okay, we found in fact that the region of convergence for that signal was from minus b up to the plus b, or between minus b and plus b, right? So that was a two-sided signal. So again, based on this expression, we cannot tell what type of signal it is, but if we know the ROC, then we can exactly specify the signal. So we see from the previous side, although we have this expression, right, and we also know the pole zeros, right, that it has two poles at -2 and -1. In spite of this, we can construct three different signals. Why? Because depending upon the ROC, region of convergence, we can, right? So if the we say it's a right-sided signal, right, so it has the ROC to the right side, that includes the imaginary axis. So that means for right side, for the right-sided signal of this particular case, the Fourier transform also exists, right? And then we said the second case is this one, that we say, okay, this is a left-sided signal, and the ROC is all points that are greater than less than -2. Again, the third expression, the third distinct signal that can be reconstructed from here is that we say basically the ROC is between -2 and -1. So that means although the expression is same, but based on the description of the ROC, we can say that basically there are three distinct signals. Okay, so the expression alone is not sufficient to describe a signal in the Laplace transform. You also need to know the ROC, so depending upon ROC. So hope this gives you the idea. So with this, we end the lecture for today, and we'll see you in the next lecture. Allah Hafiz. Okay, although it's it's end of the lecture, but I just wanted to show you all the three ROCs on the same slides, right? So here you can see one is this ROC. One is this one ROC, right? The second one is this one, and the third one is this one. So I hope this gives you the idea. So here are some of the Fourier transform of elementary signals. So maybe you go through them. Okay, see you in the next lecture.